finish is just fundamental of fluid mechanics, very fundamental from the beginning of concept to the carbon equation. Okay, and then for the part 2, we would like to apply all the knowledge we have, and try to solve some of the physical problem. Okay, so first one I would like to review a little bit, for the part 2. Part 2, for the chapter 4 and chapter 6 and 7, all relate to the part 2. But the chapter 4 and chapter 6 and 7, they are different. Chapter 4, they are talking about the so-called potential flow, And before the potential flow, we were talking about ideal fluid flow. What's ideal fluid? Ideal fluid means inviscid incompressible. That's the ideal fluid definition. So based on the ideal fluid definition, inviscid and incompressible, our carbon equation can be simplified. First, the continuous equation, you know that because incompressible, our continuous equation reduced to what? Divergence U equal to 0, or partial UK, partial SK equal to 0 in a tensor notation. That's the continuous equation. And Navier-Stokes equation, we have a very complicated Navier-Stokes equation due to the implicit assumption of the ideal fluid. Our equation reduced to Euler equation, and this is Euler equation. So in the Navier-Stokes equation, we have additional viscous term here. However, all the viscous term due to the implicit assumption, our viscous term is a drop. So this is a so-called Euler equation. Without any viscous term. And this is in the vector form, this is in the tensor form. So for a lot of the hydrodynamics, especially hydrodynamics, I mean the hydrodynamics mean deal with the liquid. The medium is liquid. And they're using this equation, and to solve a lot of physical problems. So sometimes we call this equation of hydrodynamics. But it's just instead of didn't consider viscous term only. Well, here, give you the kind of classification of the fluid function and of the category of the fluid. So we start from the continuum fluid mechanics. You have to know what the definition of continuum. In our part 1, we really emphasize what kind of fluid can be regarded as the continuum. We're using the Lundsen number, remember. Lundsen number is the mean free path divided by what? By characteristic length, or characteristic length divided by mean free path, right? That's a Lundsen number. And Lundsen number is a non-dimensional number. And this number can be defined, the flow is a continuum or discontinuous. So all the fluid mechanics, traditional fluid mechanics, is based on the continuous fluid mechanics. 连续流体或连体力学。So based on the continuous assumption of the fluid mechanics, we can define the density, right? We can define the density. Density is a function of x, y, z, t, right? It's a function of location and space coordinate with time. So any location inside this flow field, we can define the density, we can define the velocity, we can define the all fluid property, including the pressure, everything. Only under the continuous assumption. Without continuous assumption, all these fluid property cannot be defined. 所以如果说没有 continuous assumption 的话，所有这些流体的性质、空间上面这些是 density、pressure、压力什么都不能定义。Only under the continuous assumption. That's really important. You have to satisfy certain conditions in order to satisfy this is a continuous fluid mechanics or not. And from the continuum, we derive the full range of equations, including the conservation of mass, conservation of momentum, and conservation of energy, right? So we got the continuum equation, Navier-Stokes equation, and as well as the energy equation. So we have the 3 basic equations, in the continuous fluid mechanics assumption. So we kind of get very hard again to reach the complete story about fluid mechanics. a basic story about fluid. But when we try to apply this, okay, continuous fluid mechanics by using the full Navier-Stokes equation, we experience some problem, as you can see. It's too complicated, this equation, not easy to solve. Okay, so some physical problem, sometimes we have to simplify our assumption. So here, in the fluid mechanics, we can divide into the viscous flow or inviscid flow. And later I can show you why we can use in the inviscid flow, okay, and by assume our fluid is inviscid, and still can get some physics, okay. Based on this physics, we still can get some useful, okay, engineering application, okay. Even the fluid is always has viscous, right? There is no fluid, always the fluid is a viscous flow, okay. But however, we can assume, we can neglect viscosity of fluid and still get some physics meaning, or this physics meaning can apply to some engineering problem. Okay, that's engineer. Okay, we are engineer. We are not physics, right? If the physics people, 物理的学家, okay, this definitely is incorrect, right? Assumption. So they will not go. But however, since we are engineer, we would like to solve some physical problem, and this physical problem we know, based on this implicit assumption, we still can get the most of physics correct. And we have to really careful which one is correct, which one is incorrect. We have to know that by using this assumption. Okay, so you have to learn this. Sometimes we have to judge. Okay, by using the assumption, we can get a full of the flow field there. Okay, and for your physical problem. However, the solution of this flow problem, is that valid? Is that really true, or is an ideal case? Okay, is that really true or not true? 它是真的还是假的？你要去判断。As an engineer. Anyway, so we were in the chapter 4 we're talking about this. In chapter 6 and 7 we're talking about this. Okay, we can define. And here is a viscous. You can divide into the laminar and turbulence. That will be the most of the course will be talking in the boundary layer, okay? Because if you have viscous effect, your next course will be the boundary layer, and boundary layer we're talking about laminar and turbulence and transition between of these two. But anyway, inviscid and viscous, they all have this, okay, kind of 4 categories, okay, kind of the classification of flow. One is called the compressible. We have a definition what's a compressible, what's incompressible. Later we will clarify this. And some flow will be related to the internal flow and external flow. Internal flow means there's a confined, like a boundary, like a flow inside a tube, inside a pipe. We call this kind of is an internal flow. Inside the combustion chamber is an internal flow. Okay. However, flow over airfoil, we call this is an external flow. Okay, so they can be divided into internal flow or external flow. Okay, both of this and this. Okay, let's talk about a little bit about review a little bit what's the compressible, incompressible. Okay, so continuous equation for incompressible fluid. For ideal fluid, we call this ideal fluid is an incompressible fluid. In your undergraduate, right, you are talking about the incompressible fluid is rho is equal to constant. Yeah. But in the graduate school, this is no longer true. Okay, rho is equal to constant is question mark here. Okay, question mark means it's true, but it's not always true. Okay, for the incompressible fluid, it's not, the definition is not rho equal to constant anymore. If you are a graduate student. Okay, so the correct answer will be d rho dt will be equal to 0. If you follow a fluid particle and to see its density change or not, okay, if this density didn't change with time, okay, follow a fluid particle, okay, because inside the flow, rho may not be constant because you have in the, okay, I have raised an example called stratified flow. You remember that stratified flow. Stratified flow. Okay, this is spatial meaning for the density is not constant. Okay, then density is function of the space. Okay. But even density is not constant, it's not equal to a constant anymore. But still, for the stratified flow, okay, we can see this kind of flow still is incompressible flow. Okay, even density is not a constant. Density is not a constant. Okay, change with location and change with time. Okay, for this stratified flow. In the ocean, 在海洋流里面 okay, we have a stratified flow over inside the ocean because we have a different concentration of salt and all this density change okay, inside the ocean flow. However, ocean flow still can be regarded as incompressible flow. Okay, that's spatial one of code. If you want to study the ocean or the atmosphere engineer, okay, 地球科学, okay, they were talking about a lot of this. Okay, if you go into that field, okay. So the right definition for incompressible will be changed to this instead of this. Remember, okay. And the continuous equation I just okay will be a divergence. Okay, velocity of a divergence is equal to 0. Divergence u is equal to 0. Okay, that's the continuous equation. Navier-Stokes equation. This is full Navier-Stokes equation. Right? We derive that very okay in the chapter 1. Right? Chapter 1. The end of chapter 1. Okay. We have this equation. We call it the full Navier-Stokes equation, without any assumption. Okay. Viscosity. Okay. If a viscosity. Okay. So here under incompressible flow assumption, divergence u is equal to 0. So as you can see here, our full Navier-Stokes equation reduced because this term, partial UK, partial SK drop, right? And this term here, okay? And what else? Only this term only, right? This term here. And the rest of term, it will be like this. The 1, 2, yeah. Okay? So this is only consider incompressible fluid. Our full Navier-Stokes equation reduced to this. If you have additional assumption, for example, incompressible with constant viscosity, and this mu viscosity no longer is a function of xi here, so they can take out of this derivative and become like this. This is okay. And then if you do that, you can see we have for this term here, we have partial ui, partial xi. Again, under the incompressible flow assumption, this partial ui, partial xi is equal to 0 because of continuous equation. So our equation on right hand side will become like this. That's you are most familiar with the Navier-Stokes equation. Okay? 所以这个是你们以前常记的 Navier-Stokes equation. Okay? Okay, so that's under the incompressible with the constant viscosity. Okay, you can reduce to this because of here we also drop. Okay. Finally, if you have an incompressible implicit, that means you have ideal fluid. Okay, and ideal fluid, this term, okay, can be dropped because viscosity equal to 0. So we reduce the full Navier-Stokes equation reduced to what? Euler equation. Okay, that's it. Anyway, so that kind of give you a little bit review. We was from here, okay, we assume this is ideal fluid in the chapter 4. However, when you assume the flow is ideal fluid, okay, our boundary condition have to slightly change. Original for the full Navier-Stokes equation, okay, non-state boundary condition is satisfied, right? We have to say that. What's the definition of non-state boundary condition? Non-state boundary condition means, okay, velocity on the wall, okay, and then should be equal to what? It should be equal to your boundary velocity. So this is your fluid velocity. This is your boundary velocity. Okay, if your boundary didn't move, this is equal to 0. Right, that's non-state boundary condition. Okay. So if you do that, this is vector equal to this vector. This is the fluid velocity. This is the boundary velocity. Okay, so this should be equal. So we have the two components: normal to the surface, tangential to the surface. Normal to the surface velocity should be the same. Tangential to the surface should be the same in order to satisfy this non-state boundary condition. Okay. However, since we don't for the ideal fluid, okay, we neglect the viscous term, right? So our boundary condition cannot no longer satisfy non-state boundary condition anymore, because only viscous term, okay, because the viscous effect, okay, can prohibit the flow from slipping along the solid boundary. Okay, that means the tangential velocity, this velocity is equal to our boundary tangential velocity because of viscous effect. If you don't have viscous effect, this tangential velocity may not be equal. So the boundary condition of ideal fluid flow will change. Okay, we only have what? We only have a normal to the surface velocity un is equal to capital Un. That means our normal to the surface direction, our fluid velocity will be equal to our boundary velocity in the normal direction only. However, tangential may not be equal. Okay, here we have a tangential velocity should be equal because of non-slip bound condition. However, for ideal fluid, due to we neglect the viscous term, okay, our boundary condition, this one should be changed. Okay, this tangential velocity will not be. So we only have a normal velocity. Okay, normal to the surface velocity should be the same as a boundary. Okay, that means there is no flow across the boundary. That's only true for the invisible flow. Okay, boundary condition means there is no flow across the boundary, right? But the flow can be tangential to the boundary with a flow field, with a velocity. Okay, this velocity will not equal to 0 because we don't have any viscous effect to confine it. Okay, so based on this, we also can see the surface of our solid body will be a straight line because our flow will be tangential to what? To the solid boundary. So when the boundary is a tangential velocity along the solid boundary, that means this solid boundary surface is a straight line. Okay, in the invisible flow. Okay, so that's the boundary condition change. Okay, when we drop the invisible, when we assume the invisible. Okay. So here is okay. Ideal fluid, we just mentioned about ideal fluid. What happens if we have an ideal fluid and also the rotational flow? Okay, that more constraint, right? This flow is more constraint. Additional constraint is the rotational flow. Okay, rotational flow means there is no vorticity. Okay, so due to the Kelvin-Helmholtz theorem, we in the chapter 2, in the chapter 3, I remember. Our ideal fluid is invisible, incompressible, right? Plus the rotational, so we have I cube, right? So the ideal fluid mu is equal to 0. And if we have the conservative body force, that means our body force can be represented as a gradient of G. G is a scalar field. And our fluid density is incompressible. Okay, for example, this one of special case. The rho is a constant all over the flow field. Rotational, that means our vorticity equal to 0. Okay, so based on the Kelvin-Helmholtz vorticity theorem, our gamma dt is equal to 0, and gamma definition is our circulation. It also can be integrated with the surface integral of the vorticity within that area. Okay, and we can define a small area with the circulation, the delta gamma, and we do this the delta gamma dt, and as you can see, we did that before. And here is the first term is our vorticity change with time times our delta A. The other is our vorticity dot times our d delta A dt. So this one, since this is always true, right? The gamma dt equal to 0. So this is also always true. So for this, you can have this equation. Okay, if irrotational means there is no additional. Okay, there is no additional flow motion. Okay, and there is no vorticity. I'm sorry. So for the irrotational assumption here, d omega dt, because this is vorticity equal to 0, so this equation should be equal to 0. So if you follow a fluid particle, your vorticity under the irrotational flow assumption, what does this mean? our vorticity will not change. That means, however, since irrotational, we don't have any vorticity in the flow, right? So this is always equal to 0. That means all the flow is equal to 0. All the vorticity equal to 0. Okay, didn't change with time. You can also get from the vorticity equation. This is vorticity equation. Under the implicit assumption, this is implicit. This viscous term is dropped. If under the irrotational flow, omega equal to 0, so d omega dt equal to 0. The same conclusion as this. Okay? So if you follow a fluid particle as it flow, as you can see, okay, the vorticity of fluid particle will not change because the d omega dt equal to 0. Right? That's the physical meaning of the omega dt equal to 0. If you follow fluid particle and this fluid particle vorticity will not change in the ideal fluid, okay, and irrotational flow. Okay. Okay. So before we go into the so-called ideal fluid plus irrotational flow, for this ideal fluid irrotational flow, if you combine these two assumptions, you usually call it a potential flow. OK， 所以如果说你们有时候看书，也就叫这种流场叫 potential flow， 这个特殊的一个名词给它。OK， 它是个 ideal fluid， that means implicit incompressible with irrotational. So implicit incompressible irrotational is equal to potential flow. Okay, and for the potential flow, okay, there's a sum of the very beautiful mathematics behind this potential flow. Okay, even we simplify our flow, become implicit incompressible irrotational. Okay, and a lot of mathematics you can play. Okay, for example, since irrotational flow, our vorticity equal to 0. Right? This is all over the flow field. Okay? And as you can see, if our velocity can be represented as a gradient phi here, because the gradient phi curve of gradient is always equal to 0. That is vector identity. 它是个向量恒等式。Okay? 一个 curve 一个 gradient always equal to 0. Okay? 所以 therefore, okay, we always can represent our velocity field to become a scalar field phi here, and take a gradient of this scalar field to become this velocity field. And that makes us mathematics simpler. What do I mean simpler? Usually we have to deal with a vector. Vector has 3 components, right? U, V, W, 3 components. However, if we can using only one scalar field, and once we can solve this scalar field, we know all the velocity. If right, mathematically it's simpler. We only have to solve only this phi here, and this phi we have the spatial terminology for this is called velocity potential. This phi is a velocity potential usually. Okay, so if we can find the velocity potential for this flow field or for this physical problem, okay, we take a gradient phi, we can find a u vector. That means you can find u, v, w at different direction velocity once we find this scalar field. Okay, make your mathematics more simple. We don't have to have 3 components: x component, x direction component, y direction, z direction. Right? We only can solve one scalar field here. Okay, if you do that, okay, so our mathematically here, u velocity can be using the velocity potential to represent. So since our continuous equation here, divergence u is equal to 0. That's for incompressible assumption. So it's a potential flow, one of the conditions for the potential flow. So as you can see, gradient divergence u equal to 0, and this u can be represented as a gradient phi here. So that will become the Laplace phi here. So Laplace phi equal to 0. That's our Laplace, one of the Gaussian equation. We don't have to solve what the Navier-Stokes equation anymore. You see what my point? Mathematically simpler, even we can neglect all the Navier-Stokes equation. We don't have to deal with the Navier-Stokes equation. We have to deal with on this equation. Okay, once we can solve this equation and we can find the phi, and this phi take a gradient, we can find the velocity. Right? Easier, much easier. Okay? So this is our Gaussian equation later for the potential flow. Potential flow Gaussian equation reduced to Laplace equation. Laplace phi equal to 0. Okay? So this is we have to solve the gradient phi, Laplace phi equal to 0, this equation. However, we still have the boundary condition have to specify, right? Then the boundary condition again is what? Is there is no flow across the boundary, right? Tangential is not, but there is no flow. So we have the partial phi partial n as a u dot n. U dot n as normal to the surface velocity, okay, will be equal to our boundary velocity dot n. That means that's boundary normal velocity. Okay, this is our solid boundary moving with the velocity. Okay, if this u is equal to 0, that means our solid boundary didn't move. That means our normal to surface velocity is equal to 0. That's one of special case for this. However, sometimes our boundary may move, right? May move. Okay, when the boundary is moving with this velocity, but we have to satisfy our flow on the boundary. Normal direction of velocity component will be equal to our normal direction of our boundary surface velocity. Okay, so this is only the boundary condition we have to satisfy, and this can be represented as a partial phi partial n equal to u dot n. Okay, that's normal to the surface velocity equal to partial phi partial n. That's our boundary condition. So we have the Gaussian equation. We have this boundary condition. We can solve all the physical problem we have. Okay, here is the conclusion for this chart, for this show. Okay, so as you can see, we make a big deal of simplify our equation from the full Navier-Stokes equation, right? And eventually we were talking about a potential flow, and as well, potential flow is an incompressible implicit irrotational, right? 3I, right? I is I cube, right? So you will have to remember I, okay, is I cube condition, okay? And compare with incompressible implicit flow, okay? This is ideal fluid only. This is with additional irrotational flow assumption. So this is potential flow. As you can see, our Gaussian equation different. For the potential flow, we have a Laplace equation. Okay, we have a Laplace equation. For the ideal fluid here, I should mark the ideal fluid here. Ideal fluid is an Euler equation. Okay, this is reduced from what? Navier-Stokes equation. Only drop the viscous term. Okay. To solve this problem, okay, once we solve this problem, we have to solve. Okay, if we can find once we have this phi, okay, scalar field, velocity potential, okay, have this phi, we can take a gradient of this, get the velocity. Right, we solve this and then take a gradient, get the velocity. Okay. However, if you want to solve this equation, 你要去解这个方程是 Euler equation. You have to solve what? You have to simultaneously solve for your velocity field as well as pressure field. Pressure also relate to the velocity. Okay, 压力场、速度场在同时解。It's not easy, right? Not easy. Here we decouple already, right? We can solve this velocity potential, take a gradient, get you velocity. And from velocity, we can also using what? So-called Bernoulli equation. Remember, implicit incompressible, we have a Bernoulli equation, okay, in the chapter 3. So this is unsteady Bernoulli equation. Okay, once we know the phi, this is all known, right? The G is already, this is a body force. So we can using the Bernoulli equation to solve for pressure. So the potential flow, the beautiful thing, one of the beautiful thing for the potential flow is velocity and pressure is decoupled, right? Mathematically, 它可以分开解. Here we have the velocity field and the pressure field have to solve simultaneously, 同时解. Okay, here we only have to solve this velocity potential, get the velocity field using the Bernoulli equation, get the pressure field. Step by step. Okay, we don't have to solve this complicated velocity, complex equation, and simultaneously solve for these two variables. Okay, so that's another beautiful for the mathematically. Okay, boundary condition slightly different. Okay. Okay, this I think I make a mistake here. Okay. this should be the viscous flow. Viscous flow is non-slip boundary condition should be. So here we are assume it implicit. I think I make a mistake here. There should be the set actually.